Thank you. So welcome to this talk about Arcilator, new, fast, and cycle-accurate hardware simulator in CIRCT. So let me briefly give you an introduction to CIRCT for those of you who are not familiar with it yet. So CIRCT is a MLAR-based, modular, and library-based compiler toolchain for hardware development. So you can use it to build a compiler to take a front-end language like System, Verilog, Chisel, or even C++ or MLAR upstream via HLS to compile it to a chip. It can be an ASIC, can be an FPGA. But essentially, building a chip is not that simple. So you need to do a synthesis, simulation, formal verification, and a lot more. So taking a closer look at CIRCT, we have some front ends. So a production-ready Chisel compiler, some Python entries, some HLS, a very experimental System Verilog front end. Then we have the core dialects, HW for defining module hierarchies, comp for combinational logic, and seq for sequential logic. And those are taken as input for the backends. There we have some export Verilog, which is the only production-ready backend to print the core dialects to System Verilog and use it in external tools like, for example, Verilator, which is an open-source cycle-accurate simulator. And now also Arcilator, which we're going to talk about in this talk. So Verilator is a really great simulator that is claims to be very fast and is widely adopted. And now, why do we actually care about simulation? So in the software world, you want to test your program, you give it some test input, you basically just hit enter and you get a result and you can compare against what you expected. But in hardware, you would need to tape out the chip, hook it up with the surrounding hardware to feed it some test input and check against the results. So that's why we simulated CIRCT. So we give the simulator a hardware description and a simulation test bench, which is essentially a wrapper around the hardware design that interacts with the software environment, reads some file from disk, and provides the input to the design or implements some EXI protocol, memory interface, or whatever. And this LLHDSIM, which is also a backend in CIRCT, uses that design. But what it can also do is compile the hardware design and the simulation test bench ahead of time using a so-called simulator generator to a binary that is then the actual simulator specific to that hardware design. And then you can run that binary to get some VCD trace, for example, given some input program. And Arcilator and Verilator are simulator generators that use this design. So we can also simulate at various levels of abstraction. So we can have a full system functional simulator like Gem5, which you can use to simulate a whole SoC on a high level. Then when you're happy with that simulation, you can actually implement the hardware at an RTL level, simulate it, either just functional or with timing information, so with cycle accuracy. And that's where Arcilator, Verilator, and LLHDSIM are positioned. But you can also go even further and simulate on the gate level. So that image, for example, shows a 4-bit adder in just simple gates. So we are focusing on RTL level cycle-accurate simulators in this talk. And in this category, we can also distinguish between a dynamic schedule and a static schedule. Dynamic schedule means that it is computed at runtime what parts of the design should be executed, which is used by the by the classic event-driven simulators, like also LLHDSIM. And there, if you have some integer unit, some floating point unit, and you do some integer addition, you would only execute the integer unit and not evaluate the floating point unit because it doesn't compute anything meaningful. So that's the only thing that is executed. But for a static schedule, you need to compute the whole design every cycle, because you don't know at compile time what parts of the cycle are actually used. So if you have the same program, you would simulate both the integer and the floating point unit. So that is the design of Verilator. So when you start at the core dialects of CIRCT, you would use, for example, Virtual to generate the system Verilog. Then Verilator compiles that to C++ code, and then you use, for example, Clang to compile it to a binary and link it against the test bench. But that uses system Verilog and C++ as intermediate representations, which are both very complex languages and not really intermediate representations that you want to use. The LLHDSIM, the old simulator in CIRCT, directly compiled to LLVM IR instead, but it did so in a single pass, and it covers a really big semantic gap, which means that it is difficult to implement optimizations that should reside in between those layers of abstraction. So what Arcilator does, it also compiles from the CIRCT core dialects to LLVM IR, but it inserts 4 additional IR stages. Those stages are marked in green here. So from top to bottom, we have a data flow representation representing the design in so-called register transfer arcs, making the execution schedule explicit. Then we have a deferred control flow, which already has allocation, load, store operations, but they have special semantics in that the loads always load the state from the previous cycle, and the stores form the new simulation state for the next cycle. After that, those load and store operations are made immediate, which means additional temporaries are inserted to such that stores to a state are not visible to a load in the same cycle. And after that, we can compute a global simulation state from all of those allocations to optimize for cache locality. But now let's take a closer look at these lowering stages by looking at this running example of a circuit that computes the sum of Fibonacci numbers. So that's how it looks like in the CIRCT core representation. I don't expect you to read and understand all of that, but what you can see here is an instantiation of the module on the right. You can see some registers, and you can see some combinational logic in between. So that's how it would look like as a block diagram. You can see the nested module in blue, and you can see the registers as the big dark gray boxes. And what Arcilator does, it starts at those registers, traverses the dev use chain backwards until it reaches the next register or function module boundary, and groups those together and outlines them into so-called arcs, which are basically pure functions. That's what it looks like then. It also consumed the registers on the way and annotated them as latencies on the arc operations. So you can see here that arc A, D, and C look basically the same modulo the constants inside. So what we can do is we actually name the instantiations of those arcs. We call them states in that case. And then we do the dedupe, so we now only have arc A for all 3 of them. And that's how it looks like then in the textual IR. So you can see these 5 state operations on the bottom. Those represent those green boxes that we saw before. And these arc define operations on the top represent the contents of the green boxes. So what we saw now is, so optimizations you can do on this level are dedupe that we just saw. So if you have 2 arcs that are the same, we can just remove one of them. We can convert a set of combinational logic to a lookup table. Of course, it would be more than just a simple AND gate, but yeah, we can also do register retiming by simply moving the latency attributes around. And we can do loop rerolling. So a series of multiplications could be just put into a for loop, which could help instruction cache locality. We can also vectorize arcs. And then we can compile them to the next lower stage. So for now, let's get rid of the contents of those arcs because those are not relevant anymore for the next lowering stages in this example. But of course, they're still present in the IR. So the deferred control flow stage is the next one. You can see that we have these allocated states, en, a, b, c, and out, and loads. Loads will start with an L and stores start with an S. Those have the semantics that a store, if you store 5 to state A in cycle 1, and then store 3 to state A in cycle 2, and then read from state A, you read the value you stored in the last cycle. Optimizations we can do on this level or are particularly suited to this level are converting muxes to conditional branches, which can be helpful if you have a big fan-in tree and you typically only compute one particular one of those, so you could keep a lot of computation there. You could group resets and enables, which are often just, many designs just have one or a few amount of resets or enables. And then we schedule the execution graph of the arc states. So you can see time from left to right. So that's the execution schedule that is determined for this example here. And what you can see is that we store a value to A and then load from it in the same cycle. So to lower that to the next stage, to make those stores and loads immediate, loads and stores like LLVM, load and store operations, we would need to insert a temporary. And then after the last read from those from this state A, we can transfer the value we stored in the temporary to the actual position of A. On this level, we can optimize the memory layout. So you can determine the order in which you store the states. You can insert some padding to make sure that you have good cache locality. Although that optimizes data cache, and usually the bottleneck in simulators like that is instruction cache. Then for the next lower state, we collect all the allocation operations, put them in one single simulation state, and then we basically replace all those allocation operations with get element pointer operations to get this base pointer that we pass on to the arcs, which are now lower to call operations. Optimizations we can do on this level is splitting the ArcIR into multiple LLVM files, because opt and LLZ are just single-threaded. So if we just leave them in one file, it would take a while to compile them. And then that's what the LLVM IR we get as an output. You can see that there are a lot of those get element pointer, which are the converted allocations, some load store operations, and the combinational logic in between. To evaluate the simulator, we chose 3 configurations of Rocket Core, which is written in this Chisel generator language, and 2 configurations of Boom, which is a more complex core. So we saw that Arcilator performs up to 4.3x faster than Verilator on the small rocket core design, and up to 1.9x faster than Verilator on the largest design we tested. We also saw that Arcilator produces smaller binaries. That's mostly because we have this ARC deduplication pass, which is more effective than just only running CSE, and you can't really deduplicate modules. So we are up to 4x. We produce up to 4x smaller binary. For compile time, we saw that we still perform worse than Verilator because we did not implement all the optimizations I mentioned before. Specifically, we do not split the design into multiple LLVM files, which means we are essentially just using single-thread compilation, while Verilator produces multiple C++ files that can be compiled in parallel. So while Arcilator is a simulator, I think ArcIR, specifically the first stage I presented, could also be useful for formal verification and for synthesis. And I think some people are looking into using ARC for formal verification. I'm really interested in what they find and if they find it useful. But to conclude on Arcilator, I have presented a library-based modular design, which means that you can just bring your own optimization paths that you can insert into Arcilator for research, for testing, so you don't have to generate or write your whole simulator from scratch. We have shown performance of more than 2x faster than Verilator on the designs we tested. We have an IR that converts cyclic hardware to a DAG of register arcs, which form an explicit execution schedule, which is easy to work with. And we have shown that we can simulate full RISC-V cores that are non-trivial. So that concludes my talk, and I'm happy to take any questions.
All right, so we've got a little bit of time for questions. We've got 2 microphones in the center of the room, so if you have any questions.
Does it support only 2-state like Verilator, or does it support 4-state?
It only supports 2-state at the moment.
Okay.
Because, most, like the comp dialect in CIRCT mostly supports 2-state only.
And what is the primary reason it is faster than Verilator?
So we do a bunch of optimizations. I'm not sure.
You haven't
what are the most effective,
drilled into like why Verilator is slower. That's also open source, right? You haven't compared.
Arcilator
is coming from.
Yeah.
Where is the performance coming from? Do you know? Versus Verilator.
So we do more deduplication. Like simulators like that are usually bottlenecked by instruction cache, so by the CPU front end. And reducing the binary size has a big effect on, reducing the pressure on instruction cache.
And what do you use for test bench? Is it?
We ran the Drystone benchmark, which is an integer-only program.
Okay, thanks.
And then over there.
Okay, so thank you. A very interesting talk, and I declare an interest because I'm one of the developers of Verilator. But have you got benchmarks where you take system Verilog as the input rather than Chisel as the input?
So the problem here is that we compile from the core dialects of CIRCT, and we only have this very experimental system Verilog front end. Yeah. So we are not able to get in complex and big system Verilog designs yet. But it will be really interesting to see how.
Because I suspect you're getting some of the speed from the fact you're getting rid of all these intermediates.
Yes.
So I think that's one thing. The other one is a technical question. One of the things that makes Verilator slow is when you get combinatorial loops apparently appearing, and they're caused by, there's not actually a loop there, it's just you combine various registers into a single integer, and different bits of the register are connected in different ways, but if you look at the register whole, you appear to have a loop. And actually breaking up registers and getting rid of the loop and flat warnings in Verilator makes a big difference in performance. Is that something you do?
We don't split up registers themselves, but we inline all the modules because our new unit of reuse are the arcs. So, if you have an instance of a module, it could also look like a combinational loop, right? So
Yeah.
those would be eliminated.
Alternative, do you have any figures for how much time you spend settling combinatorial loops?
We don't have any combinatorial
Okay,
loops.
I mean, that'd be an interesting...
Those are all eliminated. Those designs don't have any combinatorial loop, actual combinatorial loops.
So that would be a good one for you to test, because combinatorial loops famously do not do well in cycle-accurate simulators like Verilator, so that'd be a good test. Okay.
Okay, yeah, that's
Great
very
work.
interesting.
Very
Thank you. Thank you for bringing that up.
And there's another question at this microphone.
Thanks for the talk. Really, really cool. Glad to see this is making progress. I kind of missed when the deduplication happens, because I would expect, like in the front end, it looks like when you're generating the initial arcs, that you're not taking into account the commonality that happens with the shared logic between two, that fans into two different registers, and that you're generating them as separate arcs. But then in the end, maybe wasn't clear to me whether you were doing deduplicate, at what point you did deduplication, or whether you were waiting till the end and then just relying on CSE. I think you sort of half answered the question. I didn't quite get it.
So at the stage where we convert from this module-based design to those arcs, we basically do kind of color coding of the fan-ins, and parts of the fan-in that are used by multiple registers are put into their separate arcs, actually.
Okay.
And then we outline all constants of the arcs so that we pass them as basically like function arguments. And then we do deduplication, which then finds more cases.
Got it. Cool. Thank you.
Hi. On page 50, you show that at least for rockets, the larger the size is, the speed up is smaller. Because I know nothing about hardware. Do you know why? Because it got really, really close.
So you're asking why the speed up gets
smaller? Yeah.
So yeah, that's actually an interesting question. So one thing I could imagine is that, because we produce a smaller binary size, the effect, like the benefit we get decreases because we might not feed all the code into the instruction cache anymore and stuff like that. But I'm not exactly sure why.
Sorry, but I saw your binary size decrease. That's the next slide.
Yes.
But those are converging
the
same way the other ones.
Oh, I see. Yeah. Okay. Thank you.
I see another question.
Yeah, okay, thank you. I wanted to give other people a chance. So when you compile the Verilator models, do you compile with PGO and do you compile with OS? Profile guided optimization. Because if you're compiling with O2, Verilator models will go dreadfully slowly for the cache reasons, which is why you always compile a Verilator model with OS or OZ. So when you
use the O3 option.
It'd be good to see that graph if you compiled the Verilator models with OZ or OS.
O3.
No, OZ. Make them small.
Okay.
But it's all when you use Verilator models, first thing you learn is compile for small because they'll go faster because they are classic cache busters. And that's why profile-guided optimization makes a big difference as well. So you could easily flip all those performance results if you compile. And I'm not sure. And then the question would be, does it have the same effect on Arcilator? 'Cause if you're doing the same sort of thing, you may have exactly the same problem, and you may find that using profile-guided optimization and compiling with OZ makes your Arcilator models go faster.
What was the question?
So I'm asking you, which optimize when you build your you generate your when you do your compilation, are you effectively compiling for minimal code size?
So in Arcilator, we don't specifically compile for minimal code size. We just do this deduplication, which is just the default path. And when we invoke LLZ and opt from LLVM, we also used O3. So,
So it's more of a comment and recommendation. Try doing your measurements, compiling with those.
yeah, that would be
Out of
really
interest of
interesting.
time, let's take that discussion
Yeah, we'll take it offline. Yeah.
Let's give a round of applause for our speaker, Martin.